send all the data to all the validators one by one. So this is most robust design. Why? Because no one in the world wants a successful block propagation as much as the leader does. So that's why this is the most fault-tolerant design. And the most efficient design is somehow like to use the bandwidth of all the validators kind of equally. So this is one hop, and the other one has more than one hop. So I will talk about broadcast strategy, encoding systems, and data transmission protocol for our RaptorCast system. Broadcast strategy, I'll be talking about the kind of like how the data flow, if it's structured or not structured. Encoding system is about how to generate those chunks, and I will also briefly talk about data transmission protocol. So I talked about the most fault-tolerant design, which is one-hop design. The leader sends all the transaction and the block to all the validators just one by one. So why this is not good? So imagine such scenario. This is a very reasonable assumption, like having 1,000 nodes and block size 2 megabytes, 5,000 transaction, bandwidth, thousands gigabit per second, and the leader must be honest. So that would take around like 16 seconds to send that block to all validators one by one. So in a high-performance blockchain, probably that's not something acceptable, right? So we are looking for something below a second or even less than that. So how to address that? We will add one more hop. So the issue with that one, the bottleneck here is bandwidth. Only these numbers are based on the bandwidth. So forget about the encoding latency, decoding latency, network latency. That's not included here. So it's only the bandwidth. So the idea here is to use the bandwidth of all the validators somehow. So the most efficient way is to use all of them if they have the same bandwidth. The best approach is to use them equally. So I'll show it here, the idea. Imagine we have a block of transactions. We apply encoding system, which I will talk about later. And we will end up with, let's say, k chunks of data. These are encoding symbols. So then the next step, what the leader does is to assign k over n chunks to each validator, and then each validator will rebroadcast those chunks to all other validators. So assume we have, let's say, 100 validators and 3,000 chunks. Each of them will get 30 chunks, and each of them will send those 30 chunks to all other validators. So, and also note that we do not kind of like divide the data into small parts and then encode each part separately. That's what like other approaches like Turbine or Rotor do. So there is an issue with this design. If we assign each validator equal chunks, there is an issue with that one because the validators are staked, and we don't know how many of them are Byzantine. We have an assumption, and this is the assumption. The total stake of Byzantine nodes does not exceed 1/3 of the total stake. That's the assumption that we have. But we are not talking about the number of Byzantine nodes. There could be a case that maybe 90% of the nodes are Byzantine. At least I'm just talking theoretically, not in practice. For example, take a look at this stake distribution, like 10, 20, 20, 17, 1, and the rest of them are 1, and the total stake is 100. And you can think of these numbers as percentage, 10% of the stake, 20%. You can see that the first 4 validators will reach to supermajority, which is 67%. And the rest of the validators can be all Byzantine nodes. So according to most of the BFD assumption. So in that scenario, if we have, let's say, thousands chunks, and if we assign these chunks equally to each those validators to rebroadcast, we will send each of them 27 chunks. And we will end up of using like will end up missing and losing like 90% of the chunks if 33 out of 37 validators are Byzantine here. So what would be the best approach then if we cannot equally assign them? We will assign chunks to each, the leader assigns chunks to each validator based on their stake value, proportional to their stake values. So this is the equation, and then we round up. This roundup is also very important. If we don't do that, we cannot prove the fault-tolerant property. So that's an example. So assume we have 8 chunks of data. That's the encoding chunks that the leader has. So, and that's the stake distribution, 2, 3, 2, 1. And the sum of the stake value is also 8. The leader preemptively generates 4 extra backup chunks in case the roundup happens. We don't want them to run out of encoding symbols. So, and then assign, let's say in this example, the leader has generated 12 chunks, and then assign 2 chunks here, 3 chunks here, 2 chunks here, and 1 chunk here. And then they rebroadcast those chunks to each other. So at the end, they will all get all the chunks. So this example is when we actually need the roundup. So the same scenario, we start with 8 encoding chunks. And again, the leader generates 4 more chunks in case the roundup happens. And you can see that here in 2 examples, the roundup happens, and we will use like 10 chunks out of these 12 chunks. So, and then the next hop, they will rebroadcast those chunks. They are kind of in charge of broadcasting those chunks to all other validators. So far I talked about the strategy. I hope the strategy is clear. So there is a leader, he generates some chunks, and then assign those chunks to the validators based on their stake value, and then they rebroadcast those chunks to the rest of the validators. So now I want to talk about the encoding system. The encoding system tells us what we are looking for here is, imagine we have like k source chunks. So, and we generate, let's say, k prime encoding symbol. We want to be able to decode successfully with high probability given k plus epsilon chunks. So how does it reflect in blockchain system? So imagine we have a 4 megabyte block and we set each chunk size to 1500 bytes, which is close to a UDP packet size. And then we will end up with 3100 source chunks. So if we divide 4 megabytes into 1500 bytes chunks, we will end up with around 3100 source chunks. And then we generate 10,000 encoding chunks. I will talk about why 10,000, why not 4,000, why not, how do we choose the redundancy here? I will talk about that one as well. But for now, imagine we generate 10,000 chunks. We want to be able to decode successfully given 3100 plus small amount of extra chunks. So the encoding systems that we are using is called Raptor code, R10 variation. It is based on LT decoder, but there are it has 2 improvements over LT decoders. LT decoders, I will tell you one example here. There are 2 improvements. First improvement is over when LT fails to decode, Raptor codes can still continue decoding, and also it has some pre-coding which helps to the robustness of the decoder. Let's briefly talk about the LT decoder. This is the encoder. So imagine we have 5 source chunks. So if we have a data, we divide it into 5 different parts: C1, C2, C3, C4, C5. And we have a degree distribution that's actually is in the paper of the LT Luby transform paper. Based on this degree distribution, we select some chunks and we XOR them together. Very simple. So here the randomness is 1, and we select one of these chunks randomly, and that's it. If the randomness is 3, we select 3 of them randomly and we XOR them together. So that was the encoder. So S1 to S5 are our encoding symbols now. Now the decoder works as follows. It's called peeling. So we start with just the degree 1 symbols and we peel all the degree 1s. And if we don't have any degree 1, then we just fail. Here we have 1 degree 1. We just assume we have this one, and then we XOR C1 with all those encoding symbols containing C1. So now this one becomes degree 1, and then C3 and C5 and C4. So, but it's not always going to be as nice as this one. You can see if this is another example. It starts, but at some point it gets stuck because there is no degree 1 left here. Or here, even though we have like 6 encoding symbols, we cannot decode because there is no degree 1. This could be easily solvable with some Gaussian elimination, but that's not how LT decoder works. So the idea is like to keep it simple with just peeling. Peeling sounds very simple, like just degree 1, just XOR them and use them. That's how we want to do that. So what Raptor code does is, the idea is inactivation decoding. So idea is when you get a stock somewhere, you just imagine you have a degree 1. So for example, here we get a stock, we assume we have C1, and then we start the peeling, and at the end we go back and try to solve the remaining Gaussian elimination. And also it has like LDPC and HDPC to help with the robustness. Some pre-coding, some very long, high degree encoding symbols to kind of include all possible chunks, at least once. All right, this is a very important slide. This is how we choose redundancy. So remember I said like 10,000. So how does that number come from? Should we go with 2x, 3x? How do we choose that number? So the goal is to address these 4 issues. First is packet loss. We want to address packet loss. We want to kind of like exclude the leader stake value from the total stake. We also want to address Byzantine fault tolerance issue, and also helps the decoder, that epsilon that I mentioned above. We kind of want that one to be included. So to give you some intuition about that equation, that's where 1.1 is addressing the extra chunks for the decoder. Those 2 L and L prime in the denominator are for the packet loss, and that equation is just, if you set the stake value of the leader to 0, it gives us like 3/2, which is 1.5, which is just a very typical Byzantine fault tolerance. And if the leader stake value is close to 3/2 of the network, 2/3 of the network, then it goes to infinity. So it makes sense. If the leader himself has 2/3 of the stake value, then it's meaningless probably they need like infinite number of like chunks to kind of like have the robustness. There is no honest nodes remaining, and all the remaining nodes could be potentially like theoretically malicious. So here is some numbers. You can see for a very reasonable case where the leader stake is around 1%, 5%, and the packet loss is around like 1%, we have around 1.72 redundancy, which is a very, very acceptable number as compared to like Turbine. They have like redundancy of 2. All right, so this is the last slide, and it's about the data transmission layer. That shows the structure of like our each UDP packet. It contains a Merkle proof, so still we need the authentication of each of those chunks, right? So when a validator receives a chunk, he needs to make sure that this chunk is coming from the original leader. That's why we have a Merkle proof and some header and chunk header. You can see that some like the details here. I won't go over them. And there we will be around like 1268 bytes remaining for the data. All right, thank you very much. Any questions? Sure.
adopt the UDP rather than TCP? Is it because of mainly for latency?
Yes, absolutely. So TCP is kind of like makes it almost impossible because of all the back and forth. So what it gives us is kind of like if you haven't received a packet, so then you can ask for it. But we kind of try to address that with the redundancy. So to kind of like avoid that latency, we want to just only use UDP and address that with kind of like redundancy. And also another thing is just kind of the parity check that the TCP has. We also don't care about that one because there is a signature on each of those chunks. If any of those bits flips or any tampering with the kind of the packet happens, the signature verification will fail, and they immediately understand that this is not a valid packet. So there is no reason to use TCP here in this.
Which means that if there's a packet missing from the UDP, that is recovered by the raptor code decoding.
Yes, there is. Yeah, that's a good point. So, basically, there is no like actual ID or any kind of. So what we care is here. We want to be able to have a successful decoder in case of having 3100 plus epsilon, any 3100 plus epsilon out of the 10,000. So we don't care, like there is no ID here. So that's what encoding gives us. Yeah.
So I think like in the context of modem and the context of like autobahn, the data transmission is a little bit different because in this case we are doing like one-to-end propagation. But like in autobahn, I think like they are doing more like end-to-end gossiping on the data display vision. So do you think how do you have any idea how you can use this for this like end-to-end gossiping layer as well when they are not transferring the block entirely, but like transferring like transaction each by one?
That's a good question. In my opinion, the reason that this is useful here for one-to-N is we don't want to only rely on the bandwidth of one leader, and that's why one-to-N, I showed the slide, it takes like 16 seconds. And when we have end-to-N structure, we can use this, but we are already using the bandwidth of everyone. So it's not like it's giving us too much, this structure. So what I don't think there is that much gain of using this structure because the bandwidth is already being used. So it's not like this one because in one-to-N system, the bandwidth of the validators are not being used. But in that, I think in Autobahn, in end-to-end, everyone's bandwidth is kind of engaged. So I don't think it's actually that much useful for that scenario. Yes, thanks. All right, thank you very much.